So let's start with the exercise questions. First question is, we need to find the range of frequency of light that is visible to average human being. The wavelengths are given. So this is the first one. Now the wavelengths which are given is 400 meter to 700 nanometer, 400 nanometers to 700 nanometers. So now how to find the frequency? So we know that the frequency is equal to velocity over wavelength. So it will be, the speed of light in vacuum is 3 into 10 to the power 8 meter per second over 400 nanometer, that is 10 to the power minus 9 meters. Similarly for this part, 3 into 10 to the power 8 meter per second over 700 into 10 to the power minus 9 meters. So after solving this, you will get that this frequency comes out to be 7.5 into 10 to the power 14 hertz, and this frequency will come out to be 4.3 into 10 to the power 14 hertz. So the frequency range is 4.3 into 10 to the power 14 hertz to 7.5 into 10 to the power 14 hertz. In the second question, we have the wavelength of sodium light 589 nanometer. We need to find its frequency in air, its wavelength in water, and frequency in water, and the speed in water. So this is the second one. So what do we have? We have wavelength of sodium lamp light 589 nanometer, which can be written as 589 into 10 to the power minus 9 meter. Now first part, frequency. So frequency in air. So the speed of light in air is approximately equal to the speed of light in vacuum. So we will use the speed of light in vacuum only. Okay, this formula. Let me write this C so that you cannot, you do not get confused with the velocity. This is the speed of light in vacuum. Upon 589 into 10 to the power minus 9 meter. So after solving, you will get 5.09 into 10 to the power 14 hertz. Then we need to find the wavelength in water. So this can be found out by this relation. So refractive index is inversely proportional to the wavelength. So which means refractive index in air will be inversely proportional to the wavelength in air. Refractive index in water will be inversely proportional to the wavelength in water. So let's take the ratio of these two things. So what we will have? We will have this thing like this. So 1 over 1.33 equal to 589 into 10 to the power minus 9. So after solving this, you will get that the wavelength in water will be 443 into 10 to the power minus 9 meters or nanometers, 443 nanometers. Now frequency does not change. Remember, always remember, frequency of light does not change when it travels from one medium to another medium. So the frequency will remain same in water and in air. So this is the same frequency that we will have. The wavelength change but frequency does not. Next we need to find the velocity. So again this can be found out by this relation, inverse relation between refractive index and velocity. So again taking the ratios. So what we will have, once we take the ratio, we will have this thing. So velocity in water will be mu a into Va over mu W. So after putting all the values, you will find that the velocity comes out to be meters per second. In the third question, index of refraction of fused quartz crystal is given 1.472 for light of wavelength 400 nanometer. and it is 1.452 for wavelength 760 nanometers. So we need to find the speeds of light of this wavelengths in the quartz. So this is the third one. So again we know that refractive index is inversely proportional to the velocity. So we have two cases. So we can write like this. So 1472 over 1, because air's refractive index is 1. 3 into 10.8, because in air the velocity is 3 into 10 to the power 8, and velocity in this medium, so it will come out to be 2.04 into 10 to the power 8 meter per second. This is for the 400 nanometer wavelength, and for 760 nanometer wavelength this will be the formula. So it will be 2.07 into 10 to the power 8 meters per second. So directly using this relation. In the fourth one, the speed of yellow light in a certain liquid is given. We need to find the refractive index. So this is the fourth one. So the refractive index can be found out by this formula: velocity of light in vacuum over velocity of light in the given medium. So it will be 3 into 10 to the power 8 over 2.4 into 10 to the power 8, which will give us 1.25. So the refractive index will be 1.25 in this medium. In question 5, two narrow slits are there emitting light in phase and are separated by some distance 1 centimeter. Wavelength of light is given and interference is observed on a screen placed at a distance of 1 meter. So the capital D is 1 meter. So we need to find the separation between the consecutive maxima, and can we expect to distinguish between this maxima? That is, will the consecutive maxima have different intensities, different widths or not? And we also need to find the separation between the source, which will give a separation of 1 mm between the consecutive maxima. So this is quite straightforward. By directly applying the formula we can find the values. So what are the given quantities? Slit width is 1 centimeter, distance between the slits is 1 centimeter or 10 to the power minus 2 meters. Wavelength is 5 into 10 to the power minus 7 meters, and the distance between the slit and the screen is 1 meters. So first part, separation between two consecutive maxima, it is also called the fringe width. So fringe width is lambda d over d. So after putting the values, we will obtain 5 into 10 to the power minus 5 or 0.05 millimeter. Second part, now the fringe width is given, that is the distance between the bright or maximas. So it is minus 3 meters. So we need to find the distance between the slit and the screen. 5 into 10 to the power minus 7 into 1 over d. So from here you will be able to find d will be 5 into 10 to the power minus 4 meters or 0.5 millimeters. So directly by using the fringe width formula we can find out everything. The separation between consecutive dark fringes in YDSE is 1 mm. Screen is placed at distance of 2.5 meter. Separation between the slits is 1 mm. So we need to find the wavelength of the light. So this is the sixth one. So what do we have? We have fringe width. Separation between maxima or minima is the fringe width. Then distance between screen and the slit is 25 meter. Distance between the slits is 1 mm, 10 to the power minus 3 meter. This is 2.5 meter. So beta equal to lambda d over d. We did something wrong here. This is 1, this is capital D, remember. Yeah, so it will be 10 to the power minus 3 equal to wavelength into 2.5 meter over 10 to the power minus 3. So after simplifying, you will get that the wavelength is 4 into 10 to the power minus 7 meters or 400 nanometers. We have a double slit interference experiment. Separation between the slits is 1 mm, wavelength is given, distance between screen and the slit is given. We need to find the distance of center of first minima from the center of central maxima, and how many bright fringes are formed in 1 centimeter width on the screen. So this is the 7th one. Distance between the slits is 1 mm, 10 to the power minus 3 meters. Distance between the slit and the screen is 1 meter. Now the fringe width is 0.5 mm. After solving, beta equal to d lambda over d 0.5 mm. Now the distance between center of first minimum from the center of central maxima. So look, the situation is like this. So let's say this is, let me draw it again. So let's say this is a central maxima. So distance between central maxima and this first minima. So this is half of the fringe width. Okay, this is half of the fringe width. So beta by 2, that is 0.5 over 2, which will give us 0.25 mm. Now in the second part, we need to find the number of fringes. So number of fringes will be equal to the distance over the fringe width, beta. So it will give us 20. So there will be 20 fringes. Okay, it is quite simple. 0.5, 0.5, 0.5, 0.5, 0.5. So how many? 20 will be there in 10 mm. In the 8th question, we have a YDSE experiment. Two narrow vertical slits placed 0.8 mm apart and illuminated by same source of yellow light. Now how far are the adjacent bright hands in the interference pattern observed on the screen 2 meter away? So this is the 8th one. So here in the 8th one, what do we have? Distance between the slits is given. Wavelength is given. Distance between the slit and the screen is given. So by this we can easily find fringe width. It will be 1.47 into 10 to the power minus 3 meter or 147 mm. In question 9, we need to find the angular separation between consecutive bright fringes in YDSE with blue-green light of wavelength 500 nanometer. Separation between the slits is given. So in the YDSE experiment, the angular separation is given by this formula, beta over d or lambda over small d. So what do we have in this question? Lambda is given 500 nanometer, which is 500 into 10 to the power minus 9 meter. Small d is given distance between the slits. So directly lambda over small d, that is 500 into 10 to the power minus 9 over 2 into 10 to the power minus 3, which will give us 250 into 10 to the power minus 6, or in other words 25 into 10 to the power minus 5 radians. And in degree, if you convert in degree, it will be 0.014 degrees. In the 10th question, we have a source emitting light of wavelengths 480 nanometer and 600 nanometer. It is used in double slit interference experiment. Now the separation between the slits is given and the interference is observed on a screen placed at 150 centimeters from the slits. So we need to find the linear separation between the first maximum corresponding to the two wavelengths. This is the 10th one. So here what do we have? So we know that the position of any maxima minima is given by this formula. For the first maxima, n is equal to 1, that is lambda d over d. Okay, so first maxima is next to central maximum. So lambda is given as 480 nanometer, and in second situation it is 600 nanometers. Capital D is 150 centimeters, that is 1.5 meters. Small d is 0.25 mm, that is 0.25 into 10 to the power minus 3 meters. So first situation, it will be 1.5, 480 into 10 to the power minus 9 into 1.5 over 0.25 into 10 to the power minus 3. So from here y1 will be equal to 2.88 millimeters. Similarly for y2, it will be 600 into 10 to the power minus 9 into 1.5 over 0.25 into 10 to the power minus 3. So from here y2 will come out to be 3.6 millimeters. Now 11th one is a very interesting question and quite common. White light is used in YDSE. Find the minimum order of the violet fringe which overlaps with a red fringe. So in the 11th one, we have to talk about the overlapping. So let's say let mth bright fringe of violet overlaps with nth bright fringe of red light. So we have to tell them when they will overlap after the central maxima. So it can be found out by m by this formula, okay, y n lambda d over small d. So for the violet it will be m lambda d over d, and for red it will be n lambda d over d. This is for violet color, this is for red color. So here ym will be m into 400 nanometers into d over small d, and here n into 700 nanometer into d over small d. So ultimately this has to be equal because this both will be bright fringe, it is to be found out. So this will be equal like this. So from here you will find that m over n is 7 over 4. So this means m will be 7 and n will be fourth one. So the 7th of the violet and the 4th of the red will overlap properly. Similarly, you can go on 14th one and 8th one, 21st one and 12th one, okay, and so on. In the 12th question, we need to find the thickness of plate which will produce a change in optical path equal to half the wavelength lambda of light passing through it normally. Refractive index is nu. So this is the 12th one. Now optical path difference, optical path difference is given by mu minus 1 into the thickness, and it is given that optical path difference has to be lambda by 2. So mu minus 1 into t. So from here thickness will be lambda over 2 into mu minus 1. This will be our answer. In the 13th question, plate of thickness T made of a material of refractive index mu is placed in front of one of the slits in YDSE. We need to find the change in optical path due to introduction of the plate, and what should be the minimum thickness T which will make the intensity at the center of fringe pattern to be 0. So this is the 13th one. So first part, change in the optical path. So change or difference in optical path, it is given by, as discussed above, by this formula. Then we need to have dark fringe at center pattern. We need to have dark fringe at the center. So this means that the pattern should shift by 1/2 of a fringe. What does this mean is that we have a pattern like this. So let's say this is the central part. So what do we want? We want this minima to come here. So what do we have? We need to shift it by half the width of the fringe. Okay. So mu minus 1 into t. How to shift? How much to shift? Lambda by 2. So thickness will be lambda over 2 mu minus 1.